In this video, we will continue to talk about the properties of water and its importance in biochemistry. Water is a neutral molecule with a slight tendency to ionize. It can dissociate into H pluses and OH minuses. The dissociation of water is a rapid reversible process, and the equilibrium is strongly to the left. So for the KEQ, which would be the concentrations of the products over the reactants, which can be illustrated as such, the KEQ is going to be a really small number because the concentration of water is going to be large compared to the concentration of the H pluses and the OH minuses in solution. Now we use the abbreviation H plus, but H pluses don't actually exist free in solution. In reality, hydronium ions are in solution. And this is what a hydronium ion looks like. It's an oxygen bound to 3 hydrogens with a positive charge. But for simplicity, we'll just write H plus. Now the way this happens is you really are going to have 2 water molecules involved in the ionization. And the oxygen of one grabs the proton on the other. So this would be the base. This would be acting as the acid. And as a result, you get H3O plus hydroxide. But the important thing to know here is that whenever you see H plus, we are really talking about this H3O plus species. Proton hopping can occur between a series of hydrogen-bonded water molecules, and it will result in an extremely rapid net movement of a proton over a long distance. So starting with this hydronium ion, and then you have a series of water molecules, that H plus is getting transferred to the next water molecule, which then loses a proton to get transferred to the next molecule, and so on and so forth, all through the chain. Proton hopping can play a crucial role in many biological proton transfer reactions, such as the movement of hydronium ions in the cellular matrix. Here you see the equilibrium constant expression that I had on the previous slide. What we often use is the ionic product of water, which is simply the KEQ term multiplied by the concentration of water. And in this, Kw equals the concentration of hydronium ions times the concentration of hydroxide ions, which will always equal 1 times 10 to the minus 14 molarity squared at 25 degrees Celsius. M stands for molarity, which is a measurement of concentration, and that is the moles of the substance per liter of solution. In pure water, the hydronium and hydroxide concentrations will equal each other, and they will each be 10 to the minus 7 molar. So using the Kw equation, if you know either the hydronium or the hydroxide concentration, you can always figure out the other variable. The pH of a solution is the negative logarithm of the hydronium ion concentration. The pH plus the pOH must always add up to 14. And we can get to this equation from the Kw expression using some logarithmic math. So if we take the negative log base 10 of H plus times OH minus, that will equal the negative log base 10 of 10 to the minus 14. Now, whenever you have a log expression of two things multiplied together, that is rewritten as the summation of those two things. So this becomes the negative log base 10 of H plus the negative log base 10 of OH minus equals the negative log base 10 of 10 to the minus 14. And the negative log of H plus is just pH. The negative log of OH minus is pOH, and then the negative log of 1 times 10 to the minus 14 is 14. When you have a neutral solution, the H plus will always equal the concentration of OH minus, and the pH is 7 at 25 degrees Celsius. Now at different temperatures, the pH of a neutral solution will vary slightly. So for example, at 0 degrees, the pH of a neutral solution is about 7.5. At 100 degrees, it's a little bit above 6. And the reason for that just has to do with the extent of ionization of water, which is temperature dependent. This table shows the pH scale and relates pH and pOH to the concentrations of hydronium ion and hydroxide ion. So if your hydronium ion concentration is 1 or 10 to the 0, then the pH is 0 because the negative log of 1 is 0. If the hydronium concentration is 10 to the minus 1 or 0.1, then the pH is 1. So notice that the pH is simply the exponent but with the reverse sign because we're taking the negative log of it. Now if you look through the table, you'll see that the pH plus the pOH for all these values always equals 14. And if you know the hydronium concentration, you can always figure out the hydroxide concentration using the Kw expression, and vice versa. So if you just have one of these four values, hydronium ion concentration, pH, hydroxide concentration, or pOH, you can get to all of the other three. This figure shows you the pH of some common liquids. So HCl, which is very acidic, would have a pH of 0. Then gastric juice is also highly acidic. That has a pH of around 1.5. Black coffee is fairly acidic. Then when we get into blood, that is right around 7.4. And baking soda is basic, and then we can become increasingly basic when we get to household bleach and sodium hydroxide. We will often be dealing with weak electrolytes and weak acids. So this is acetic acid, also known as vinegar, and it's a weak acid. And what that means is that it just partially dissociates in water. So the equilibrium expression here is going to lie mostly to the left. So acetic acid is going to mostly be in its reactant form, not in its hydronium ion and acetate form. The extent of dissociation is determined by the acid dissociation constant Ka. So Ka is simply the hydronium ion concentration times the conjugate base concentration divided by the concentration of the starting acid. And Ka is related to Keq because it's just Keq times the concentration of water. The Ka is going to give us an estimate of the strength of a particular acid. The greater the Ka, the stronger the acid. Which makes sense because if Ka is bigger, then the concentrations of these products is greater, which means more ionization is taking place, and the reaction's lying further to the right. However, if the Ka is small, that means that the dissociation isn't happening to much of an extent, and therefore that's a weaker acid. Because the strength of an acid is simply how well does it dissociate into hydronium ions and its conjugate base. Now, if we know the Ka, we can actually calculate the pH of a solution, but we do have to do some algebra. So suppose you are asked, what is the final pH of a solution when 0.1 moles of acetic acid is added to water to a final volume of 1 liter? So you want to use your Ka expression, but since we don't know how much of the conjugate base and the hydronium ion we have, we're just going to use the variable x for that. So when we put this into the Ka expression, we get x times x over 0.1 minus x, because whatever amount of x you produced, that came from your starting acetic acid, so this would no longer be 0.1 moles anymore, it would be 0.1 minus x. And then you set that equal to the Ka value, which is known. Now you rearrange the equation to get x squared equals 1.74 times 10 to the minus 6 minus 1.74 times 10 to the minus 5x. And then you can put that in the quadratic equation form and solve for the quadratic equation. And when you do that, you get x is equal to 0.001310 moles. And we mentioned it's a final volume of 1 liter. So for the concentration, moles divided by liters would just be this number divided by 1, which is just that number. And then you take the negative log of that, because that would be the hydronium ion concentration, to get to pH. Now, I'm not going to make you use the quadratic equation because we can use an easy simplification. So what we're going to assume here is that the amount of X is very small relative to the amount of the starting weak acid concentration. So we're going to just say that X is negligible to the starting concentration, and we're just going to eliminate the 0.1 minus X and use 0.1. So that simplifies things a great deal. Now we can use this Ka expression again, but instead of going through the quadratic, we just say x squared equals 1.74 times 10 to the minus 6. Take the square root of that. We get this value for x and this pH, which is almost identical to the one we got on the previous slide using the quadratic equation. This approximation works for sufficiently weak acids and bases, and you can double check when you get your final answer that the X value is indeed a lot smaller than the starting value, and feel confident that your simplification worked fine. So the Ka value is a measurement of the acidity, but instead of using Ka values, we more commonly use pKa values just because it gives us easier numbers to work with. So instead of working with 1 times 10 to the minus 5, we could just work with a pKa of 5. And here is a table that shows some various pKa's. So if you have a bigger Ka, that would lead to a smaller pKa. So the smaller pKa indicates a stronger acid. The bigger pKa indicates a weaker acid. Notice here that there are also monoprotic acids, diprotic acids, and triprotic acids. A monoprotic acid just has 1 acidic proton that it can give up. A diprotic acid has 2, and a triprotic acid has 3. And there's a Ka value for each of the protons that can be given up. So for a triprotic acid, such as phosphoric acid, you actually have 3 different Ka values. So if we look here, the first Ka value would refer to this equilibrium, the second Ka value would refer to this equilibrium, and the third Ka value would relate to this equilibrium. And then the pH scale also shows how the pH is changing depending upon the acid and the equilibrium in effect. Buffers are very important in biochemistry. They are mixtures of weak acids and their conjugate bases. Buffers resist changes in pH. When the pH equals the pKa for a particular weak acid, there is a 50-50 mixture of the acid and its conjugate base form. The buffering capacity of an acid conjugate base system is greatest when the pH is equal to the pKa, and it's lost when the pH differs from the pKa by more than 1 pH unit. This is a titration curve for acetic acid. So in this, what we're doing is we're adding equivalents of hydroxide, which is a strong base, to a solution of acetic acid, which is a weak acid. On the y-axis, we have the pH. As you add hydroxide, it will react with the weak acid. So my hydroxide is my base, so that's going to grab the acidic proton from acetic acid, and it will convert that acetic acid into its conjugate base and will form water. So as you add hydroxide, it's going to be undergoing this acid-base reaction. So notice here the pH is pretty low at the beginning because you just have acetic acid, so it's an acid solution. Then it starts rising as you add hydroxide because you're getting rid of some of the acetic acid and converting it into the conjugate base. Now notice in this titration curve, there's an area that's shaded in blue that's relatively flat. And that area is called the buffering region. This is where the acetic acid and the acetate, its conjugate base, will exist as a very good buffer. And notice where that lines up with the amount of equivalents added. So here you've added 0.1 equivalents, and here you've added 0.9 equivalents. So between 10% and 90% titration of the weak acid, you will have a good buffer. Now, when the pH is exactly equal to the pKa, the weak acid and its conjugate base will exist in equal concentrations. Now, once you start adding more hydroxide equivalents, the pH above the 0.9 equivalents, the pH will increase rapidly. So notice that the buffering region is 1 pH unit above and below the pKa value. This shows a comparison of titration curves of 3 different weak acids. So here we have the acetic acid titration curve we saw on the last slide. And above that you have the dihydrogen phosphate weak acid. And that comes from phosphoric acid, which is a triprotic acid. So what is shown here is just the second buffering region in that titration, and then the red line would be for ammonium. So the point here is that every different acid will have its own buffering region, which will be 1 pH unit above and below its pKa. So for acetic acid, we saw what that was on the last slide. For dihydrogen phosphate, that will have a buffer between 5.86 and 7.86. And then for ammonium, that buffering region is in between 8.25 and 10.25 pH. Now, this dihydrogen phosphate buffer is important in the fluids of cells, and notice how its buffering region overlaps with the physiological pH of 7.4. So biological fluids are heavily buffered, both intracellular and extracellular fluids. And the pH of blood, for example, in healthy individuals is 7.4. And the phosphate and bicarbonate ions in most biological fluids are important buffering agents because they have pKa's in that range. Now, how do you find the pH of a solution containing a weak acid and its conjugate base? Well, we use the Henderson-Hasselbalch equation. So how do we get to this equation? So we know that the Ka for weak acid is equal to this expression. We can rearrange that to solve for the hydronium ion concentration. And if we take the negative log of each side, we get this mathematical expression. And the negative log of the hydronium ion concentrations is simply the pH. The negative log of the Ka is the pKa. And we can invert the HA and A- positions, and by doing that we're going to also invert the sign here. Let's try an example using this equation. Suppose that you have a buffer and is comprised of 0.1 molar acetic acid, which has a pKa of 4.76, and 0.05 molar sodium acetate, the conjugate base. What is the final pH of the buffer? So in the lab, you would go in and actually mix these things together to make a buffer. So the final pH, you would take the pKa plus the log of the concentration of the acetate divided by the concentration of the acetic acid. And when you solve for pH, you get a value of 4.45. Now, when the concentrations of the acid and its conjugate base are equal, the pH equals the pKa, which is what we saw with the titration curve. And mathematically that makes sense because if these were equal, then you'd have the log of 1 here, which would be 0. So in that case, the pH would equal the pKa plus the log of 1, or pH equals pKa because the log of 1 is 0. Oftentimes, water is bound to proteins, and that is essential for their function. This picture shows water bound in a proton channel of the membrane protein cytochrome F, which is part of the energy trapping machinery of photosynthesis and chloroplasts. 5 water molecules are hydrogen bonded to each other and to functional groups of the protein. The protein has a bound heme, its iron ion, facilitating electron flow during photosynthesis, and that electron flow is coupled to the movement of protons across the membrane, which probably involves proton hopping. This picture shows hydrogen-bonded water as a part of a protein's sugar-binding site. In the L-arabinose binding protein of the bacterium E. coli, 5 water molecules are essential components of the hydrogen-bonded network of interactions between the sugar and at least 13 amino acid residues. In Chapter 2, we learned about the nature of intermolecular forces, especially hydrogen bonds, van der Waals forces, osmotic pressure, and the hydrophobic effect. We learned about the properties and structure of liquid water, the behavior of weak acids and bases in water, buffers, and the importance of water in biological systems.